David Robbins TSPP Conjecture.
Okay, thank you for giving me the opportunity to speak here. Richard talked a lot about taste in mathematics, and I'm afraid that the proof that I will present does not match his taste of nice proof, but I know for sure that there are other people in the audience, or at least the birthday boy, who will appreciate that. So we should not argue about taste. So also we had heard Thierry Frankel talking about pleasure proofs. Again, if you want to read this proof, I think it's not a pleasure to read this proof, but it was a great pleasure for me to generate it. And I want to mention my collaborators, Manuel Kauers, who is also from RISC. Peter Fowler explained already what RISC means. I alluded here with the RISC symbol because I did my PhD at this institute, and I will return to it in fall, but currently I'm in Tulane. And also, this work was inspired by Norm, and he gave lots of motivation to continue and to bring it to a successful end. So, let's start to explain what is a QTSPP, because I'm sure not everybody here has heard this before. So this shortcut stands for totally symmetric plane partition, and it's just a Q version of totally symmetric plane partitions. So if you look at this figure, this is one example of a totally symmetric plane partition. So the first thing that one might ask, well, this doesn't look very plain, right? I mean, also it's projected on a plane, but this is supposed to be a three-dimensional structure. So a partition is, we partition an integer into parts, and they are arranged in the plane, and according to the integer sitting on a certain position, we stack as many cubes onto that partition. In this sense, it's a three-dimensional representation of a plane object. And the conjecture that I'm talking about is, has been raised by George Andrews and by David Robbins. That's to speak from the base of this structure. And Richard Stanley, I guess, he was the one who really made it very public in his paper, A Baker's Dozen of Conjectures Concerning Plane Partitions. Forgive me if I don't reproduce the history exactly, because this was in 1983. I was still a very small boy and not really yet interested in such things. What I have told so far is just the TSPP, so we are still missing the Q. In the Q case, what we are also interested in are the so-called orbits. And so the colors of these cubes represent orbits. If you look at the red cubes, then Robbins, for example, has the coordinates 7, 1, 1. And if you permute them, if you let the symmetric group S3 act on these coordinates, we get the other red cubes. And similarly for the green cube, this has the coordinates 4, 4, 4, so nothing changes. And if we have 3 different coordinates, we get an orbit of length 6. So in this problem, we're going to count these objects. And this counting works in the way that the number of orbits are encoded by this additional indeterminate q. So if you look at the first figure, we have no orbit at all. So this is encoded by the power q to the 0, and the coefficient is 1. So there's one totally symmetric plane partition with 0 orbits. And so in this example, I'm restricted to plane partitions that fit into a cube of size 2. And then we see that in the second example, we have one orbit giving a q to the 1. In the middle, we have 2 orbits, and so on. And there's always just one totally symmetric plane partition corresponding with so many orbits. If we go to bigger ones, the coefficients will turn out to be not constantly 1. And then, so here's the conjecture. If you look at the orbit counting generating function, so this notation just gives the number of orbits, and we sum over all totally symmetric plane partitions, then this generating function can be written as this really nice product formula. And let me introduce this notation for referring to this problem in the following of my talk. And let me also mention, if you set q to 1, you get a more classical result that just counts the number of totally symmetric plane partitions. As you observe, if you plug in q equals 1, you just get a natural number, and this gives you the number of such objects, which has been proven by Stambridge, and another proof later had been given by the previous speaker, Peter Paule, in collaboration with George Andrews and Carsten Schneider. Okay. Now we are not directly attacking the problem, but first use a classical reduction that is due to Soichi Okada. And so I represent the Okada operator, this symbol that you see here. So if you apply the Okada operator to the Andrews Robbins conjecture, what we get out is the following. We get the determinant of these entries, and now I can use the definition of the pure binomial coefficient that Dominique Foata introduced in this talk. Also, he did use it. So these are the entries in the matrix, and we are looking at the determinant. And if we succeed to prove that the determinant evaluates to this formula, which is just the square of the enumeration formula, then this is equivalent to the original problem. So this is the Okada part. So forget about that. We have already seen this. And now we apply a second reduction. We apply the C operator, which holonomizes the whole problem. So if you have a mathematical problem and you want to solve it by the computer, usually you have to reformulate it to some algorithmic framework. And this is what Doron suggested. So he takes the determinant and he gives these three identities, where first you have to pull out of the hat another function. So this function C and J is not known. So the procedure says if you succeed to find such a function such that these three identities are fulfilled, then you have proven the determinant evaluation. Why is this the case? Let me just shortly hint to it. The C and J plays the following role. Think of the cofactor in the Laplace expansion of the determinant divided by the n-1 times n-1 determinant. Then you will see that this last identity just reflects the Laplace expansion with respect to the last row. And the second one is nearly the same as the third one, just that we replace this n by an I. So we exchange the last row by the ith row, where I is different from n, making the determinant 0. And the first one just stays the normalization. Okay. This function C and J that I mentioned is yet unknown. So what do we do to get a handle on it? This is the Cowers operator that pulls out of the head this unknown function, but not explicitly, because